Let me also record it. So what I'm going to do in my 2 lectures is to give a basic introduction, and the goal is to familiarize you with some and give you some intuition about the black hole solutions in general relativity, because they will be extensively used in the talks on Wednesday and Thursday. So in today's lecture, I'm gonna just talk about the Schwarzschild solution, and hopefully tomorrow I'll get to have some time to also discuss the rotating black hole Kerr solution. So what's the Schwarzschild solution? It's a spherically symmetric and stationary solution in empty space. So the solution exists in those parts where there's no matter, and it's spherically symmetric so it has rotational symmetry about a point, and it doesn't depend on time coordinate. Actually, you are familiar with one such solution. This is one such solution, just the Minkowski matrix. But this one is without any source. This one has all these properties, but we want to make it a little bit more general. And since it is spherically symmetric, the metric which we will get to, so it is going to be sourced by a spherically symmetric mass distribution as well. So what we are looking for is the metric in the empty regions around, for example, some spherically symmetric mass. Now there's a theorem by Birkhoff which says that if you go looking for a spherically symmetric solution in empty space, symmetric solution in empty space, you will find only one kind. It will be a Schwarzschild solution, is the Schwarzschild. So in other words, this stationarity condition is not an assumption. It just comes out of it as soon as you assume spherical symmetry. But I will not be proving Birkhoff theorem. That will be a little bit more technical. Rather, I will try to motivate, but still I want to show you part of the derivation to get some idea that how the solution is coming about. So I will assume stationarity, that it doesn't depend on the time coordinate, and then see how much progress we can make. Now, first of all, one can define the concept of spherical symmetry. So that's our main assumption which is going in an inherent way without reference to any coordinates. But I'll not take that route. I will use some special coordinates where this spherical symmetry is apparent. For example, if you take this Minkowski metric, we know that how to make this spherical symmetry apparent in this case. So by a change of coordinates, which is essentially is the going into take the XYZ and transform them into the spherical polar coordinates, you get this metric. The Minkowski metric takes this form. And over here, if I take surfaces of constant r, so dr is 0, dt is 0, I end up with a metric on a sphere. You have some constant value of r, and you get this metric. And since we recognize it as metric of a sphere and of fixed area 4 pi rc square, we can compute this area using this metric. What we have in this case is that at each constant value of r and t, we have a sphere. So the space-time, you can think of it as being foliated by these spheres. So space-time is foliated by these spheres. At each t value, you will have a foliation in R using these spheres. This is true for the Minkowski case. Now, this spherical symmetry will remain there as long as I keep these spheres around, because on these spheres I can rotate and nothing changes. So my definition of spherical symmetry would be that as long as I have these spheres, foliation by spheres, then I have spherical symmetry. Now, what you can do in order to generalize this metric is that the spherical symmetry would persist if I deform the size of each of these spheres and deform the distance to various spheres. You don't have to use the Minkowski metric to compute that. So I deform those things. So what it would do, this is the deformation of the distance to each consecutive sphere. And by including this vector, I can deform the size. As long as I do not include any theta and phi dependence, I'll still retain spherical symmetry, but each sphere, I can deform its size and its distance from the origin. Now, one can ask that there would be terms like this. What about the terms like this or like this? When I have a constant r, di is 0, these terms also drop out. So can I include them over here and still retain spherical symmetry? Well, you can definitely do that. However, these terms can be excluded by a change of coordinate. So I can pick a coordinate system where these are not needed. And the argument, pictorial argument, is very, very simple. So you have two nearby spheres. And your r, now I have deformed it. It could be going in any different direction. So what is this? This is dr, so to speak. If you have a value of theta and phi here, this takes you to theta, phi, same value on the next sphere. So this is dr, and in this direction you have d theta and d phi. So this angle between dr and d theta will be controlled by these terms in the metric. This one and this one. Now I can arrange, I can rotate the sphere, use the, because at each point I can have Riemann normal coordinates. So that at that point, the basis vector are orthogonal. So I can change this coordinate, I can rotate this sphere, I can bring these in a form so that they align perfectly. The spheres align perfectly, and I have lines going like this. So that this vector and this vector are perpendicular. So I will be able to, in that case, this term will have a coefficient goes to 0, has a coefficient 0. So the most general metric would be of this form. What I have over here is those deformations which I talked about. This is the metric on the sphere. Metric on a sphere. And I'm including now that assumption about stationarity, that I have no time dependence in the metric coefficients. And the theta phi dependence only goes into this vector that is needed because of the spherical symmetry. But these all other terms will be there. But this term again can be removed by a change of coordinate. It's actually quite easy. All you have to do is define a new coordinate like this. And then this term, which appears in your metric, takes this form. It's just one line of algebra, not even two. This is this dash is derivative with respect to r. So when I put this term over here, I have a dt dr term. So by matching my f of r, choosing an f of r so that I can cancel this with this. So this cross term in r and t is also gone by a change of variable. And then I can define this scaling, call it a new coordinate r tilde, which I'm gonna again call r. I can write my metric into this form. Now, I should mention that this assumption that the metric components do not depend on time coordinates, it looks like a coordinate dependent statement, but it can be made precise by saying that you have a killing field. Killing fields are the ones which describe the symmetries of the metric. Let's say K, T, so that the lead derivative with respect to this field of the metric is 0. And this killing field is such that it is time-like at the asymptotic regions. When you have such a field, then you can define coordinates so that the metric does not depend on that coordinate. The metric components do not depend on that coordinate. So that is the fact which I am using. So you can start with this and conclude that if I need this thing, so this can be then thought of as the definition of stationarity. And I should mention that I'm taking it as an assumption, but using Birkhoff theorem, you can prove that you do not need to assume. It just comes out of Einstein's equation. Similarly, you can define I made the spherical symmetry apparent in the coordinate system, but you can start by assuming that there is spherical symmetry by taking some killing fields. Let's say for the spherical symmetry, you will have 3 killing fields, all space-like, which satisfy the angular momentum commutation relations, or SU2 commutation relations. When you have this, then you will say that that's the definition of spherical symmetry. In our case, because we made it apparent, we can write down these in our coordinates. They take certain form, not very useful, not needed much later on, but I can just note down. Similarly, there's an expression for T, and they satisfy the angular momentum algebra. And they are all the killing vector of this matrix. As soon as you come to this form, you can find out that these fields are the killing vectors. Killing vector is this definition. But if you are not familiar with killing vectors, doesn't matter. We can just keep going from this form which we have got here. And then let me mention that there will be another condition which we will require. Now we have only these guys, AR and BR. And I want both of them to go to 1. At far off regions. This is called asymptotic flatness. This is clearly a very desirable condition, because if I'm thinking of some source and I'm thinking of a solution in the empty regions around it, when I go far away, the effects of this source should be not visible, and I should recover the Minkowski metric, which I will recover if this A and B are 1. It will then just be the Minkowski metric. Now, armed with this condition and that form of matrix, I can just impose the Einstein equations. And the Einstein equations then will give us what are the possible allowed forms of AR and BR. So, as you know, as you're familiar, that the Einstein equations are these. And I'm solving them in an empty region. So the energy momentum tensor is 0. There is no matter around in this region where this metric is valid. So I can contract the Einstein equation with G mu nu. So whenever you're solving the Einstein equation in vacuum, like we are, then they can be simplified by just taking this trace. So this gives you the Ricci scalar. This is the trace of metric, which is equal to 4. So it gives you 4 times the Ricci scalar. And what you have is that R is 0. And when you put it back here, this gives you R mu nu is 0. So the Ricci tensor is 0, is all of Einstein's equations when you are in the vacuum. However, Ricci tensor is 0, Ricci scalar is 0, but the Riemann tensor is not 0. It doesn't have to be. And you have to compute these factors. You compute the Riemann tensor, and then you have to impose this. This is imposed. Now take this as a homework. It's not hard. It's lengthy calculation, but not hard. I was able to do it in not much long time. You will compute these. This one, let me write it out. This comes out to be where B dash is again derivative with respect to R. All the others are 0. These are the only surviving ones. All others are identically 0. Show this. This is the homework. I'm not even writing those, what comes out. It will just waste a few seconds. Show that if you make this combination, this turns out to be equal to this. That's what you prove by computing RTT and RRR. However, we have imposed that this is 0 and this is 0. So this has to be 0. If this is 0, then you can solve this. This just gives you so this has a solution that AB is equal to C. However, by asymptotic flatness, this A and B are functions of R. This C is a constant. So as R goes to infinity, this has to become 1. And as R goes to infinity, this also has to become 1. So this constant, I can evaluate it at infinity. So the constant is 1. If the constant is 1, then whatever these functions are, they are functions, they are not constants, but they are reciprocal of each other. And using this equation, now you put this thing, this condition over here. And using this, we have to impose this to be 0 as well. Let me see if there's something important. So when you put it this back in that, you find, again, you can just do it live. It's that simple. You get this. And this gives you, this I can write like this. This solution is this, just an integration with respect to d by dr. So that gives you A is equal to 1 plus C of R. And I'm just going to call C as minus R, capital R. This is a constant. So now I have got, because of the Einstein's equations, I've got the final form of any metric which is spherically symmetric and is valid in empty space. So this is called the Schwarzschild solution because it satisfies the Einstein's equations. One thing which one can note immediately about this solution is that it's degenerate. This R, maybe I can put an S here. I will be missing it many times. Degenerate at R is equal to RS. Because this term becomes 0, this becomes infinite. So the metric components, they blow up at this value. They don't make much sense. So, but let's see what is this R. What can we say about this constant R? So that we can find out by considering Newtonian limit. Newtonian limit, by that I mean weak field limit. Because of our asymptotic condition, it does have this form that as you go away, as R becomes large, the metric components become smaller and smaller. The deviation from the Minkowski value becomes smaller and smaller. So weak field limit is very easy to derive in this case. However, we know this, you should prove or look it up, that if I write, for example, the 0, 0 component of the metric as a deviation from its standard value, where h 0, 0 is small, then matching with Newton's formulas, give me that h 0, 0 has to be minus 2 times phi, where this is Newton's potential. And we know that in a spherically symmetric case, Newton tells us that this potential is minus gm over r, where m is the mass of the gravitating body. So matching this here, in this case over here, you have that Rs is 2gm, and since I have been using the units where c is equal to 1, if you want to match the unit, introduce the real units, you will see that to make it a length, 2gm is not a length, you have to divide by a c square. So this is the value of Rs, but the important thing is that it's proportional to the mass. So it only depends on the mass. So like matching with the Newton's case, mass of the gravitating body, if you don't want to think in terms of a gravitating body, we know that there is something in center, because if there was nothing, then the only solution is the Minkowski. So there is something in the center, or even if, well, we can go all the way to r is equal to 0, but there is some mass associated with this solution, and we can think of it from where we started, that we are looking outside a body. So it's that mass. So this Rs only depends on mass, and also very small for most reasonable masses. I'm very bad with usually with numbers, but I think if you put in the solar mass, this comes out to be about of order of a few kilometers. So because it's very small for most masses, then what happens is that if you are looking for a heavenly body, looking around, so because we know that this solution is going to be a solution for any spherically symmetric mass, outside of it, if you consider the empty space, this solution which we have found would be the solution for that body, or for the space around it, space-time around it. But for most heavenly bodies, this Rs would be inside the body. That means, and we have derived this solution with the assumption that we are in the empty space. So this solution will be modified in this region. And this solution will not be valid over there. So we will not encounter for any heavenly body this problem that this metric becomes degenerate at r is equal to Rs, where Rs is called the Schwarzschild radius. Because by the time you reach there, the metric is no longer valid. However, we can imagine we are just playing a game, that we are considering a metric which is valid all the way to r is equal to 0. Suppose that metric is valid below or less than this Rs. So all you are saying is that whatever matter is sourcing this metric is crushed, is shrunken down below its Schwarzschild radius as computed by its mass according to this formula. So if that is the case, then this degeneracy will be there. And when you have this degeneracy, that kind of solution will be called a black hole solution. So a Schwarzschild solution which is valid below the Schwarzschild radius is a black hole solution because you encounter that degeneracy. So what does that degeneracy actually do? Let's see some of the effects of it. So we have like kind of established what the solution is. Now let me try to understand the nature of degeneracy at r is equal to rs. By the way, commonly this surface r is equal to rs is called the horizon. So I'll also be using this word, horizon. I want to understand it, and I want to understand it by seeing that what happens as different things approach the surface, or they go inside or they come out. What is the physics involved? And in doing so, I'm also trying to understand the nature of these coordinates. As you are familiar that in GR, it's a big problem to understand that what do the coordinates actually physically mean. You can look at very complicated looking matrix, but in the end, they may be very simple. They may even be flat space. It's just because the theory is valid in any coordinate system. So I want to understand these coordinates as well. But the way I have written these coordinates, if you hover, if you are a body and you stay at r is equal to some value r naught, and theta is equal to some constant, same is true for phi. So in a sense, the way we have constructed the coordinates, you are standing like that in this coordinate system. It's the space diagram. And if you want to make a space-time diagram, this is our t plane. This is r is equal to rs. And this is your world line. Some constant value of r in this coordinate. So these coordinates are also given a name. They're called the Schwarzschild coordinates. So in this case, if this is your world line or someone's world line, then we know that the proper time measured by a clock held by this person is just equal to minus the times the metric. So that means that the proper time would be dt. So it's less than this coordinate, which we have been calling the time coordinate. It's not really measuring the time by some stationary observers, which are stationary in these coordinates. However, this becomes dt. They match as r goes to infinity. So t, the Schwarzschild time t and the proper time are same when you are far, far away. So here's your again TR plane. This is your RS. For an observer which is very, very far away from the source, from this Schwarzschild radius, this T is equal to the proper time. But someone close to the origin has less time elapsed on their clock compared to T. And as R approaches RS, d tau is 0. So that means all it's saying is that no time, proper time is not elapsing with the coordinate time t. So in a sense, this variable t is way too fast. It just keeps moving without any changes in a clock which is sitting right over here. So something is probably wrong with this t variable. It's not saying that the time stops. It's just saying that the clock time is not matching with the time which is appearing in our metric, although it matches far away, but it doesn't match when you go close to the to this horizon. Also, if I make these slices of constant t, and from the perspective of the guy sitting here, if he starts giving these points the same times as he's measuring here, then he will conclude that the time elapses here, but the clock, because we know that this clock, this t tau is matching with the t's. So if he assigns the same times over there, according to this time, which is at the faraway clock, the clock at the horizon is not moving at all. So this guy may interpret, or you can say, for a faraway observer, a clock near horizon is slowing down and stopping at horizon. But I don't know how useful this interpretation is. We can try to see what do these clocks, a person who is going in, what happens to them. Does the time stops for them or not? For that, we need the trajectories of particles. And actually, the way I will do it, it will also be with a slight change valid for light. There's a slight difference between particles, massive objects, and massless objects, how they behave. So trajectories of particles and light in this geometry, in this black hole geometry. So how do you find these? Obviously, you need the geodesics. And the geodesic is this. Where this is the for velocity of the particle. This is describing the path or trajectory. So these are hard to write down even, but we can get, because of the symmetry, there are various conserved quantities involved. And it actually is not very hard to derive them if we go about them more cleverly. So first of all, these equations you can derive through this action principle. We know that the geodesics are the ones which maximize the length along the curve. So geodesic is that curve along which the length is maximized. So this is the length. And in case of, if I normalize, which you always do, to -1, then these guys, they become the 4 velocities. And in that case, the length is just equal to proper time, which is how I'm writing over here. And then what you can do is that this variation is actually just the variation of the quantity inside the square root. And now I'm changing this parameter lambda to tau. So you can think of it just like an Euler-Lagrange equation. You have an action and you have a Lagrangian and you have a time, which is not just t, which is not the time of Schwarzschild coordinates, is the proper time of the particle whose trajectory you are finding out, d tau. And here, the Lagrangian is given by this guy. So suppose we want to look for a radial geodesic. That means along this, theta and phi do not change, they are constant. So I can write it out, this Lagrangian. This would be just involved these two terms and I can actually pick up these metric components because I know the metric. And this is the derivative with respect to tau. I'm denoting it by a dot. R dot square. So using this, you can very easily derive the Euler-Lagrange equations, which just says compute this. So for example, there's this Euler-Lagrange for the t variable. Euler-Lagrange says that if you take the next derivative, total derivative of this quantity, since the Lagrangian doesn't have any t dependence, any tau dependence inside it, so this will be equal to 0. And that gives you a very nice formula, a very useful one. So I should write it in a box. When you take another derivative of this with respect to tau, that is 0. So that means this quantity is a constant. Now using this, I can now finally find many interesting things about what the particles do in this geometry. So for example, I can start from this, that these are normalized, these paths. This is true just by definition, I mean, not even definition, this is when you take the 4 velocity with respect to, that's the definition of 4 velocity. When you take parameterize the path with respect to the proper time, then this is what you have. So this, when I open it up, it gives me E square I had a t dot square over here, but that I replaced using this equation. So t dot is removed and I have a integral, first integral of the equation. And Now I can multiply by this factor to get this equation. So this is exactly what happens in classical mechanics. When you have a conserved you can take the first integral and you will have some kind of a kinetic energy plus potential energy, which is equal to a constant, which doesn't change as you move in that potential. So this is similar phenomena. And for example, if I have this thing, and from far away, I drop a particle. So you're dropping from infinity. I can find out the value of this constant. At r is equal to infinity, t is equal to tau. That means dt over d tau is equal to 1. So if I put it here, this is 1, and this is 1, and this is 0. So E is 1. For a particle dropped from infinity, from far away. So then this equation just becomes, and you can recognize it because you have I can, for example, multiply by this. So this is exactly as in Newton. So what we have discovered is that this solution has gravity and this r coordinate with these derivatives are with respect to the clocks carried by the falling objects. With proper time, give exactly same radial motion as in Newton. Now you can for example, you can look at this thing. So let me go back to this equation. I had derived this. When I reach, there was a 2 as well, at r is equal to rs, which is 2 gm, what happens to r dot? This becomes 1, speed of light. So the particle in these coordinates, at least in these coordinates, when it's reaching the horizon, it's not, there's no intuition, should not be that it is moving, it will not be able to cross the horizon. It's actually moving very fast. This corresponds to, also if you reverse this trajectory, that if you are coming out of the horizon to reach the infinity, you have to start at speed of light. At least in these coordinates, all these concepts about speeds, they have to be defined much more precisely, but in these coordinates. But this equation is telling me that when I'll reach the horizon, I'll be moving. And this trajectory I can integrate. It doesn't stop at the horizon. It just keeps going. Dropping from infinity, you just cross the horizon. Nothing stops you there. And for example, on the other hand, you can look from the perspective of the outside observers. What does the outside observer sees? So we have this. This is what we derived. E square. And we also had this integral, this constant of motion. So what I want to compute is the derivative not with respect to the clock carried by. So that speed was with respect to the clock carried by the falling guy. If I do it with respect to the Schwarzschild time, which is also matched with the time of the outside of a very far away observer, then I am doing this chain. And since I have both of these guys available, you can compute this chain. Now we can see that what happens near horizon. So small calculation. Let's say this is a homework. This is literally 4 lines, but I'm just trying to again save some time. You can, this R on the left hand side, I can just include a constant. That doesn't change the derivative. But on the right hand side, these E's cancel and you take out R minus 2 GM over R outside. And since you are very close to the horizon, you're assuming that R is close to the horizon, so you neglect higher order term. This is what you get. It's almost obvious from that when I'll take this common, I'll get this. So this has a very easy solution. This is just a exponential. Or R is equal to 2 GM. So as R approaches 2 GM, this must happen at t going to infinity. So it will take infinite time from the perspective of this Schwarzschild coordinate for the particle to fall in. But that's not what we are finding if we look just at the clock of the particle. So particle is falling in according to the Schwarzschild time, it just doesn't fall. It just keeps going like that. Now, apart from particles, it's much more interesting to look at what the light is doing. Light trajectories. Finding light trajectories is even easier because we know that they have to be null geodesic. So we have the same condition, this one. This is still true, except that you do not assume that your parameter for the path of the light is the proper time of the light, because there's no proper time. There's just some parameter. And on top, these trajectories have to be null, because light moves on null paths. By null, you mean that the metric along that path, metric length is 0. So from here, you can conclude that dt over dr over r inverse. So what is this saying? It says that in this coordinates, well, I can even write this thing, dr over dt. At far away, light has speed 1 in these coordinates, which is just the normal speed. But as R approaches Rs, then the speed is going to 0. So from the perspective of these coordinates, an infinite time goes through in the time coordinate and it doesn't make any progress in the R coordinate. It's just standing still on the horizon, trying to get in, but standing still. So the speed of light is going to 0 on the horizon in these coordinates. And in these coordinates, taking this, I can draw all of this, what I've said, you can see it pictorially by drawing light cones. So if I draw the light cones, this is R is equal to 0. This is T, this is R, and somewhere here is the horizon, RS. So far away, the light cones are at 45 degree because far away, this is 0 and dt over dr is just 1. But according to same formula, as you come closer, these light cones are closing off because this becomes infinite. This factor gives you an infinity. So the light cones are completely straightened out over here. So I can draw the path of the light by following light cones. So over here, far away, the light cone is at 45. But then it starts to close off. And because of that closing off, the light is becoming, the trajectory, the world line of light is becoming more and more straight up. And as it reaches the horizon, it's just traveling with it. So it never appears to reach the horizon and get into the horizon. You can draw another very important effect, which is the gravitational red shift. So as I said, that no proper time exists for light. So you have to choose an affine parameter. And since you're not bound to choose a particular affine parameter, the way you choose affine parameter is choose the affine parameter. By affine parameter, I just mean the parameter you need to parameterize the curves, light curves. This P mu is the equivalent of U mu vector for the particles. You choose it in this way that the first component is giving you the frequency, and in the flat space, the second component will give you the momentum, and the momentum, since C is 1, momentum is proportional to the frequency. So in other words, the 0th component is picking up for you the frequency. That's how you parameterize. But parameterization is obviously a choice, but frequency is something you measure. In a coordinate independent way, take this as a homework as well. This is not very hard to do. You can show that frequency, if you start with this, which is also the energy by the Planck's formula, is given by this in a coordinate independent way. Frequency is not coordinate independent, but this formula you can write in a coordinate independent way, where this has a observer, this is the word line, or I should say the 4 vector of observer who is measuring the frequency. And this is the photon path. So it will be parameterized in such a way that the observer with this 4 velocity will observe whatever frequency he or she observes. So using this formula, I can compute. So again, take an observer hovering at r is equal to some value rc. So there's this Schwarzschild radius, and the guy is just sitting here at a constant rc. Then his 4 velocity will have just the 0th component, because all others r, theta, phi are constant, so they give you 0. This is the only non-zero component. And since this is normalized, this is equal to g0, 0. So the frequency they measure is, according to that formula, over d lambda. This is coming from light path. This is coming from the u. So t dot over 1 minus 2 gm over r. But this guy, we already established that this is a constant. So the frequency is some constant divided by 2 gm over r. Now that means if a light is going, this is the radius, Schwarzschild, light path is something like this, becomes 45 when it moves away, and the light is being emitted close to the Schwarzschild radius. I'd say this is a deep, this guy is deep, this guy is out. The same light, its frequency will be measured different, given different values, because the two guys have a different u in terms of the Schwarzschild coordinates. So for the same light, you can compute this ratio. And this would be just this ratio, r deep or out. And when r out is very, very far away, then this ratio goes to 1 minus 2 gm over r deep. So what is this saying? This is saying that you can find that what would be the frequency. The frequency would be red shifting, is dropping. This is well known. This is just the gravitational red shift. But what is peculiar is that when the light starts right at the horizon, if Rs, then omega out is 0. So the light is completely redshifted away and nothing comes out. And this also collaborates with our conclusion that if the light is right at the horizon, its light cone is completely closed off, so that its path is like this. So we don't see anything outside. It doesn't come out. So one manifestation of that is that the frequency will be completely redshifted. However, all of this is in these coordinates, referring to these Schwarzschild coordinates. We can very easily show that a light, although we saw that these cones, they close off, and in these coordinates, the light keeps traveling with the with the borderline of the Schwarzschild radius, and it seems like it cannot enter the black hole. But that is just an illusion, because these coordinates are such that the t is, in a sense, very, very slow coordinate. I don't know, I should say slow or fast, one of those. Because you can compute the light's trajectory exactly. So starting from this null condition, I put in the geodesic condition, the first integral. Then I can just cancel this out, and I have an extremely simple equation. This r dot is with respect to the parameter, which is parameterizing this trajectory. So r is just plus c, and you see that r lambda has no problem. Lambda can continue, and r itself can be actually taken. You can rescale, and r can be taken as the affine parameter, and the light just simply can take any light for a finite value of lambda can have a value r for light, a value less than Schwarzschild. So the geodesic doesn't encounter any such difficulty entering into the attaining a value less than the Schwarzschild radius if you are just measuring its affine parameters on it. So this confusion that sometimes it looks like that if we follow the trajectories more carefully in terms of inherent parameters, then the trajectories do enter the black hole. But in terms of the Schwarzschild coordinates, they do not seem to enter the black hole. So how to interpret it? There's a very nice analogy which one can give, and that analogy actually uncovers a lot of black hole physics, which I believe will be also needed for Professor Ricardo's lectures. So a nice analogy. So consider Minkowski space. Now forget about all this black hole and Schwarzschild business. Consider empty space and the following change of coordinate. What change? You have this time coordinate, the time of the Minkowski. You do this change. You introduce two new coordinates, eta and rho. And the space, you write it like this. Then you can see that I can find inverse transformation by to these things. So I have x1 square minus x0 square because of the cosh and the shine. This is just rho square, while this ratio of time and space just gives me tangent hyperbolic eta. So eta is just inverse x0 over x1. So these new coordinates, rho and eta, are new coordinates. So I want to see what are the trajectories of constant rho and constant etas. So if I draw, this is the old one, this is x0, this is x1. Then I find that the constant rho things are just hyperbolas. Because this is the equation of a hyperbola. Not only that, but also you can, let me write it down. Constant rho trajectories. So it's like finding what do these new coordinates look like. How do you do it? You just look at their constant value trajectories. So constant rho trajectories are hyperbolas which are asymptotic to light cone from origin. You can just look over here. Over here, if I make a dx naught by dx1 and look at very, very far away, then this will just give me a 1. So they are all asymptotic to this light way, the light cone. So I can look at this parabola, this will also become asymptotic, all of them. And actually, they will be, you can draw the hyperbolas on the other side too. For the same value of rho, you will get the hyperbola in this region and in this region as well. So as you change rho, this is one rho. What happened? Wait. Wait. Okay. So these are constant rhos. So rho 1, rho 2, rho 3, and so on. But notice something. No matter what rho you choose, this region and similarly this region is excluded. They are not, no trajectory goes into this region. Let me call it region 1, this I call region 2, this let's call region 3, region 4. No trajectory goes into region 3 and region 4. Also, I can draw the constant eta trajectories. What are they? They are just straight lines. Look over here. Put eta is equal to constant. This is just a straight line to origin. So constant rho trajectories, which color I should use? Let's use this. I like these. These are constant not constant rho, constant eta. Eta 1, eta 2, eta 3. And when eta is infinity, you are hitting the light cone. And when eta is minus infinity, this is eta is equal to infinity. And when eta is minus infinity, you are hitting the back light cone. So again, you go from minus infinity eta to plus infinity eta. This is the whole range of eta. And the whole range of rho is 0 to infinity. You go through whole range, you do not enter region 3 and region 4. I should probably write that range of eta is plus infinity to minus infinity, and range of rho is from 0 to infinity. But none of them covers the region 1, 2, 3, and 4. I can also compute the metric in new coordinates. So d xi naught, all you have to do is take a derivative. Cos eta, and put it in this is not xi, this is x naught and x1, and put it back in your Minkowski metric, which is, so it's a two-dimensional Minkowski space which I'm considering. So this gives me, when I put these in, this simplifies to a very simple and nice metric. Maybe I should write it like this. This has a negative coefficient. This implies that eta is like a time coordinate. Because signature, I knew that it has to come out like this. This is like a space coordinate, spatial, radial coordinate, because it goes from 0 to infinity. And if I look at the light cones in these coordinates, light cones in these coordinates, they look like this. All I have to do is compute this d eta over d rho to make the null paths in the eta rho plane. So this is plus minus 1 over rho. So when rho is very large, these cones are flattened out. But it will turn out that I'm not very interested in this region. I'll be more interested in the region close to the origin. These cones are also flattening up. And when rho is 0, this is completely closed off. So this is something similar to what we saw in the black hole case. There, this property was not there, but I'll be only using it near the horizon. So this behavior is similar to what we saw in case of black holes, at least the Schwarzschild black hole. Now, these, by the way, these coordinates, these are just the coordinates. This is just a coordinate change. Same geometry in some new coordinates. These are all the artifacts of a coordinate. This closing off of cone is just an artifact of the coordinate system. So this is some geometry in some new coordinates. And by the way, these coordinates, they are called the Wingler coordinates. And I can say a few things about this. Well, first of all, I said that region 1 and 3 are 3 and 4 were not accessible. So regions 1 and 2 are called the Wingler wedges. And now I can use my physics or geometry of space because I know that this is just the Minkowski space-time. I can use that geometry to make conclusions about what seems to be happening in the Wingler coordinates. So this is x0, x1. These are the light cones. With the Wingler coordinates, you can, for example, think of Wingler observers, which are setting up this coordinate. So a guy sitting at a constant Wingler rho value is a Wingler observer. This is another Wingler observer. So these are the person who have these word lines. They set up this kind of coordinate system. And I know, let me just draw these eta. These are the constant rho. So 1, rho 2, rho 3. And these are the eta 1, eta 2. And this is actually eta is equal to infinity, and so on. Now, what is happening over here? In these coordinates, there is a horizon. If I look at this surface, what is the property of this surface? Why I'm calling horizon? If I look at anything in this region beyond this surface, so any event happens here, light from this event goes at 45 degrees because it's just the flat space-time. Anything happens here, light goes from at 45 degrees. So no light from region, I called it region 2 and region 3 ever goes out into this Wingler region 1. Similarly, no light from region 3 goes to either region 1 or region 2. So for these observers, or for these coordinates, for the Wingler wedge 1, everything beyond this surface of this light cone is behind the horizon. Nothing from there comes out. Also, if I drop a ball, there's no gravity. But a Wingler observer drops a ball. Let's say he drops it here. What's going to happen? The ball is just going to follow, because it's flat space, a straight line. But what you can say is that every ball which is dropped moves towards the horizon and crosses the horizon. Drop a ball and it falls into the horizon. Horizon has gravity, so to speak, in inverted commas. And if you shoot light towards horizon, so what will happen? This is light. If you shoot it, it's just going to cross the horizon. You can just look at it. However, for these observers, light and balls cross the horizon because that's the surface of eta is equal to infinity after infinite time. But it's obvious that this is just an artifact of the coordinate system. This is the flat space. You may be living here. This may be your world line. And you just see the light crossing the horizon after a few seconds. The ball crossing this horizon. This is not a horizon for you. It's only for these Wingler coordinates or Wingler observers. The ball crosses the horizon after a finite time. But for the Wingler observers, in Wingler coordinates, it takes infinite amount of time. So this is kind of similar to what we observed in case of the Schwarzschild. And there's obviously also a Doppler shift, because any light coming from near here, because this, if the light crosses here, this guy has a different, so let's say this light. Over here, this guy's forward velocity is like this guy's forward velocity is like this. So there will be a Doppler shift, which can be interpreted as gravitational red shift for these Wingler observers, but probably not very important. But these points are exactly what we found in case of the Schwarzschild. Now I think I'm completely running out of time. What I will do next time, I'll show you near the horizon Schwarzschild is just Wingler. And I know that the effects which I see in the case of black hole, they are like, some of them are, I can understand them in terms of this coordinate. And I know that there's no problem, there's no degeneracy at this horizon. This surface, in case of Minkowski, is just a normal surface. There's nothing special about it. And I can remove the degeneracy. The degeneracy is coming in the Wingler coordinates just because of a weird coordinate system. And I can change the coordinate to reveal that this surface is completely regular. I will be able to conclude that once I show that the Schwarzschild near the horizon is just the Wingler. So I think I should now stop and take questions. Let me stop this share because I don't know how to. Stop share. Okay, so I'll start with, there are lots of questions actually, really. So let me start with Muhammad Ali Shabazz. Shabazz, you can now unmute and then you will be able to speak.
Yeah, can you hear me?
One moment, let me turn up the speaker. Yeah, go ahead.
Now I think you can hear me.
Yeah.
So when we were calculating the Ricci scalar, it turned out to be 0. And in Junaid's talk, he said when R is constant, that is maximally symmetric space, but it is not homogeneous. The Schwarzschild matrix.
Well, the one difference is, like, one basic difference is that we are in empty space. That was not an empty space. That was with some matter present. And actually, if you were, or in that case, if you said that I want to compute a maximally symmetric solution in empty space, you will find Schwarzschild, because maximal symmetry includes rotational symmetry. It also has the
Homogeneity.
homogeneity, but you will find that if you assume the isometry around a point and you want the solution to be in empty space and have this asymptotic behavior that at faraway distances it's Minkowski, then you won't be able to get anything close, anything looking like the FRW. Your Einstein's equations will force you to consider Schwarzschild. That's the content of Birkhoff's theorem.
All
And
right,
the
all right.
difference is
And
that in that case, why you were getting that? because you do not have empty space.
Okay, okay. So not empty space and R is equal to 0 correspond to homogeneity and isotropy.
Not empty space and R is equal to 0. Yeah,
If the space is not empty and still you get a constant, then that is maximally symmetric space.
yeah, I would say so.
All right. So there is another issue. There were two types of singularities, right? R is equal to 2gm and R is equal to 0.
Yeah.
So can you just elaborate about
Well,
R is equal to 0? Can this be removed by using a different choice of
no,
coordinates?
R is equal to 0 cannot be removed because you find out that the curvature blows up over there. And so something which is scalar, which is not dependent on any coordinate system because it's a scalar. So that is getting infinite there. So this is like a something physically terrible happening. So it's like a rupture. If you think of these things as kind of a sheet, then in the space-time sheet, it's not only a curvature, it's like a hole. There's a rupture. That's why you're getting an infinite or maybe a pinch, an infinite curvature over there.
All right. So have there been attempts to remove R is equal to 0, or is just
I
going
mean,
to
it cannot be removed. This is just an exact solution of Einstein's equation, so it cannot be removed within Einstein's theory. But obviously, if you go beyond Einstein's theory, then there are hopes that you can remove it.
All right. Thank you.
So, what? How do I see more raised hands? Okay, I think there are no more raised hands. So, anyone else wants to ask a question? Let me see the written questions. So there is a question that, as far as I understand, stars and other compact objects can be modeled by Schwarzschild metric, where now RS, the Schwarzschild radius, represents the object surface. Well, actually, no. The Schwarzschild radius is inside the object surface, so Schwarzschild radius loses all its meaning. You don't need. It's not, the solution is not even valid over there because this solution is empty space solution, and as soon as you hit the star surface, it's not empty space. So the Schwarzschild radius does not come up into question. So there's a question by Aisha Mahmood. I'm gonna allow her to talk. Aisha, you can unmute yourself and speak.
Yes, I want to ask you explained the point uh, when you were discussing degeneracy.
Hmm.
You correlated Schwarzschild uh, Schwarzschild solution is valid, which is when R is less than R is something like that you discussed. I want you to please repeat that point again.
So all
Schwarzschild
I'm saying is that when R is equal to Rs, at that point, the metric components, right at that point, not below it, not above it, right at that point, the metric components are blowing up. So then that raises the question that what happens there? How do we like cross that surface? What happens at that surface? And that's all I'm saying. Because in these coordinates, that surface is degenerate, like the metric components are blowing up. So that's why we are seeing these different
you were saying that Schwarzschild solution is valid uh, outside the surface of
No, I was saying
you
that if you
related
imagine,
the Schwarzschild solution to the black hole solution. I want to listen that sentence
yeah,
again.
okay. So the point I was making is that the Schwarzschild solution is the unique solution outside any spherically symmetric body. So if you are in empty space outside a spherically symmetric body, so you are near Earth, near Moon, near Sun, the geometry is described by Schwarzschild solution. But in those cases, the Schwarzschild radius is so small that it is inside. If you compute it, the value comes out to be less than the radius of that gravitating body. And because the solution is only a valid solution for empty space, So the solution is no longer valid inside the body. And that's why the question of Schwarzschild radius does not come up in those bodies. How we define black hole? We define a black hole as some body which is so compact that its surface is inside the Schwarzschild radius. So if the surface is inside Schwarzschild radius, then the solution is valid at Schwarzschild radius because it's still empty space. And then you have to resolve that what happens at Schwarzschild radius.
Okay.
So Aisha Mahmood has a question. No, wait. No, this was Aisha Mahmood, right? Okay, I think guess there are no more questions. So let me stop here. And I'll hope to see you guys tomorrow at 1 again.